Welcome to the 21st lecture in mathematical finance. So we want to continue today to study how to solve portfolio optimization problems in, of course, um, discrete time financial markets. So I want to first recall a bit what we introduced last time, because we introduced some new notation, and then unfortunately I want to do some changes as well, because I realized that there is some inconsistency with the notation I already have introduced. So sorry for that, but I will explain it now. So what we considered so far is, well, last time we say, okay, we have here the self-financing trading strategies, because these are the trading strategies what we care about, and they have a position in the risk-free asset and in the de-risky assets. Right, so that's, and we assume that they are self-financing. And so we're not throwing away or adding any capital during our T trading periods. Okay. All right. And then we introduce some new notation that we want not even these alpha and beta, they represent the number of shares we hold. And now we wanted to, because we in the end only care in portfolio optimization, we care about the amount of money we have. So we wanted to represent just the amount we have in each of these D+1 assets. Okay, so we use phi, and phi was like, so the risk-free asset, I mean, we have again our amount in the risk-free asset and deep positions in the risky asset. So so C0 at time t is just the amount we have in terms of the risk-free asset, and well, CKT is the amount we have in terms of the risky asset. So this is so as before, K is one of the risky assets, and well, we have T trading period, so we start at 0, so we have to stop at T-1. All right, and then this is my warning. Okay, so then we express the changes of the prices in terms of returns. So what do we have? So we wanted to introduce the discounted return x tilde k at time t, which is okay, the changes in the risky asset from time t+1 to t, so t to t+1, of course, minus. So these are the discounted returns. Again, okay, we have it for k, so this is as before, and we said then the vector of discounted returns is just without the upper label k here. So this is, so if I drop the upper label here, I mean the vector of the k discounted returns. So this is stands for the discounted returns. All right, and this is what I mean here. So this is a warning, because here I made a slight inconvenient notation. So it was not wrong what I did last time, because it was the definition, but to be consistent with what I have defined already in the binomial model. So last lecture I defined this R without the tilde, but since we always use the tilde for discounted quantities, and this is a discounted quantity, let me add here the tilde. So, I mean, we only consider the discounted one, and so it would be more convenient to drop it in the sense that it's less notation, but yeah, unfortunately I defined the R already to be the undiscounted return, so I want to add here the tilde. So warning, change of notation. And this, well, then we derive the iterated as the recursion formula, how we can express the wealth we have at time t in terms of the underlying parameters. So this is the interest rate on our market, and then this is just the wealth we had at time t minus 1 plus what we get from having a position in the market, and then depending on how the returns in this trading period are, we lose or make money. And this is here again. So this is the formula we have already defined, but this here now okay. So we have seen the calculation is perfectly fine, but I wanted to change the notation from R to R tilde. All right, so this is for later references, equation 6.2. Okay. So this is what we have seen last time. And now we want to start solving or considering the portfolio optimization problem. And to make my life easier, I would like to start with the portfolio optimization problem with one trading period. Right. Okay. So this means just, I mean, we come to the general multi-period case later today. But let us start to understand, okay, how under what condition can we find a solution to our original portfolio problem, optimization problem P. And I really recall what P was, of course. So a finite market. B, so we have one risky asset, risk-free asset, and one risky asset. And as I promised you, we start easy. So we start with the time 0 and t, right? So this you have now, which is t0, and then you have future, which is t1. You can also always think in this context of buy and hold strategies, right? So, so if you're an investor, and I mean, even if the market is real time or continuous time setting, you can ask yourself, okay, I want to decide how I invest today in the market, and then I just want to hold it until my retirement. And this is, of course, if you decide a priori not to trade from now till your retirement, this is still a one period setting, right? Because we're not saying that the time index has to be 1 day or whatever, right? So you can see as this is one period is actually a rather natural setting as private investor deciding, okay, what amount she or he has to want to invest in different assets. All right, so we have a finite market with one trading period. And this allows us to simplify a bit the notation. So let me set here my R, so my interest rate is what this is actually given my formal notation by R1. So I drop the index 1. So I just will always want to drop the index 1. So R tilde is now R tilde 1. So I have some initial capital. So actually, I don't need this. And A is just 0. Right? So this is my trading strategy. So my position in the de-risky asset, which was before adaptive process, is now just a constant because it's F0 measurable, or supposed to be F0 measurable. Okay. Okay. So now if I look at my recursion formula I derived in 6.2, so you see it here in blue. So this simplifies now. So the capital, the terminal capital, which I have at time time 1, is just given by R plus R. Right? This is this. Now, okay. So this has to be with 0 plus this is an A now, and then times, so scalar product with the returns. Okay. Okay. So if I have now, if I am an investor with wants to optimize some expected terminal wealth with respect to some utility function, so I give myself now a utility function describing my preferences. So U is the utility function. And well, of course, I need to decide, what is my initial capital? So I also have an initial capital, which I want to invest in the market in the smartest possible way. So this is my initial capital. Then because I was, what is now our portfolio problem? P. So you can go back in your notes and see that what I'm writing down here is now exactly what was defined P, just in this simplified setting, in the sense that we have just one trading period. So the self-financing trading strategies are just constants. Sorry, this has to be define RD. That, and now we want to maximize the expected utility of our terminal wealth. So this is the formula I derived here. So 1 plus R. I know now what my initial capital is. So this is X0. And then I have all for A times the discounted returns. Right, so this is the optimization problem we want to solve now, which is the original 1P in this setting. And let me label it like as in the lecture notes by 6.3. Okay. All right. Okay. So this is the problem we face now. Okay. So this is the goal for the first half of the lecture today. And then the second half is to start understanding this, what happens if we have more than one trading period. All right. So you might have realized that I haven't said that this market is arbitrage free, which is somehow a necessary condition to make sense of this portfolio optimization problem. Actually, the first thing I want to show you today is that actually it turns out that there's actually equivalence between saying that this market is arbitrage free and we can find a maximizer to this portfolio optimization problem. Okay. And in order to be able to do this, I need the following lemma, which characterizes the no arbitrage condition on this finite financial market, BS. So let's start with our first lemma for today. 6.12 in the lecture notes. So let us suppose we have this market B and S, and we want that it's a finite market. And we want that the vector of discounted returns is non-trivial, so not equal to 0. So this is actually not a restriction because, well, if the vectors, if the returns are constantly to be 0, then the market is rather, this is then a deterministic market without any proper moves. So there's basically only a risk-free asset. All right, and now let us define that L, or denote by L, the smallest linear subspace, so subvector space of RT, such that my vector of discounted returns takes its values in L almost surely. Right. And so my returns, they're vector in RD, and they might not see every direction. And I want to concentrate, this is actually the direction the returns can happen. All right. What do we have? So the market here is arbitrage free if and only if Well, if I find a self-financing trading strategy, so this is basically vector A in RD, with the property that if I take this position in the risky assets, so this R, and my returns are always non-negative, right? So if I can find a position in the market which leads always to non-negative returns, well, to exclude an arbitrage, we won't need that. Then our returns have to be zero almost surely. Okay? Because otherwise, we can make an arbitrage taking such an A. And this is also equivalent to say, well, instead of considering all A in RD, well, if we take an A in L, so in the smallest linear subspace in which the vector of discounted returns can take the values, and we want to assume that this is a non-trivial vector, so it's not equal to 0, then it holds that if we take a position in the market with respect to such an A, the probability that we face a negative return coming from this investment has to be strictly positive, right? So this is the idea of no arbitrage. There should be no way to make certain profit. All right, so this is an equivalent characterization of no arbitrage in terms of these discounted returns. So let us prove this. So where do we start? Okay, let's start with the equivalence between 1 and 2. So I and 2i's. All right. Okay, we have a lot of experience with characterizing no arbitrage in markets. So first, let me recall for you, if you want to show that the market is arbitrage free, and this is a simple market, well, this is arbitrage free if and only if right, there exists an ether in RD. So this is the position in the risky assets such that well, if we take this position ether in our market and then consider the discounted, so the discounted price process, this is non-negative probability 1. Oh, sorry. Not arbitrage free. It's simpler to define what an arbitrage opportunity is. So this means basically there exists an arbitrage opportunity, and this is equivalent to consider the discounted price process here. So we just need to have an ether, which stands here for the self-financing trading strategies, such that it's the returns at time, or the gains we make at time 1 are always non-negative, and with a positive probability. We make some profit. So I hope you're really familiar, and this is an easy step for you. Otherwise, I really recommend you to go back to the notes and recall these things. Okay, so this is saying, okay, this it's not arbitrage free if we have this arbitrage opportunity here. And now let me go to a new page and observe and just go. Let's consider these expressions or the scalar product we have here. So copy paste it for you. If we consider this, so what is it? So let's write it out. This is a scalar product, which means I have my eta k. So eta is a, so these are the components of eta. Now I have, well, the eta k is the has to be multiplied with the changes of the kth asset. Right. So that's right. And well, we rewrite this as by pulling out the SK0. So and if I pull out SK0 here, what I get is exactly my discounted returns. So this is nothing else than A times the vector of discounted returns, where we take A to be the vector well, this is just AK, so AK has to be by definition eta K S0 K. All right. Okay. Oh, sorry. So what do we learn from this? So there exists arbitrage opportunity on the market here. If and only if there exists A in, well, this is this A or D such that, right, so we plug now, so we have these, we use the identity here, so we can so this A, and this is now the vector of discounted returns, and they has to be positive with probability 1 and strictly positive with the probability of this number A with a positive probability. So this is just taking this identity here and plugging it in our equivalent characterization of no arbitrage. So this is the first equivalence, and now we want to come to the second equivalence, which tells us, well, if there exists an A with gives us always non-negative returns, then the returns have to be 0, is actually equivalent by considering just all the A's in this smallest linear subspace, which is generated by the possible returns. Then the returns from such a position in the market, they have to be negative, so strictly negative with a positive probability. Okay, so let's come to the second equivalent here. So we want to show that the IR is equivalent to 3 I's. And then we have the equivalence between all the 3. So let me break here the proof into the 2 parts. So first one, I mean, they're both not super hard. So I want to apply that the condition 2i's imply 3i's. And for this, I assume that 3i's is not true. So what does it mean? So there exists now an A with A not identical to 0. And if I take this position A in the market, then the returns are non-negative with probability 1. Right? And this basically means, okay, if I have such an A, I can find an arbitrage opportunity. So this contradicts the property I. Right? So this means there exists an omega in omega such that A tilde of omega is strictly unequal to 0, because we assume that the discounted returns cannot be identical to 0. So this implies so because every omega has a positive probability, this implies is not true. So we have our contradiction. All right, that's not so hard. And the other one is also not so hard. Going back here. So basically what we want to, the equivalence, the technical equivalence now tells us that it's actually sufficient to consider only A's in the linear subspace of L instead of whole RD. So why is this actually enough? So let's assume, unsurprisingly, and that triple E holds true. If I take any vector A in RD, we can decompose it into a part which is an L. So let's call this part AL, and something which is in the orthogonal. Right. So this is part in L, and then there's a part in the orthogonal subspace of RD. So the orthogonal space to L in RD. Let me fix this notation. So L is the orthogonal complement of L. All right. So what do we see here? So if I take the scalar product of A and the discounted returns, well, this is nothing else than taking only the positions AL, right? So because everything which is in the orthogonal subspace is just eliminated, so it's identical to 0. So by the linearity of the scalar product with R, the discounted returns, R tilde, we have this identity. Well, A and T, and this means there's also the second property holds. Yeah. Right, so if you find this clear, well, because you can always decompose it, so the part which is just in which is not in L, I mean, this doesn't contribute to the scalar products here. Oh, I should use This is exactly the same. So the only observation here is, well, actually it doesn't matter what we do in the orthogonal complement of L. All right. So this proof was more small detour through linear algebra. But this small technical lemma allows us now to prove, at least from financial perspective, more interesting proposition. And okay, what do we suppose? So we suppose okay, that we want to come back to our utility maximization problem. So let us first suppose that we have a utility function. And this utility function u maps from R to R and is bounded from above. And what else do we suppose? And we have a financial market, which is finite. This is with one trading period. Finite market. With the additional assumption, which is, well, it's just in order to exclude trivial cases. So we exclude, so there should be some proper price movements going on. So the discounted returns should not be identical to 0. Okay. And then we have the following observation. So this market here is arbitrage free. If and only if our utility maximization problem has a maximizer. So the existent T in RD solving 3.6.3. So this is our optimization problem P. Right? So this means we go back to this optimization problem here. Means so with the existent our star, which attains this maximum. Okay, and this is equivalent to saying that the market is arbitrage free. So that this problem is non-degenerated, so exists really has a solution, means that the market, the underlying market, is arbitrage free. Okay. Let's prove this. Okay. So what we want to do first we assume that the market is arbitrage free, allows us to solve this utility maximization problem, sig3 or P in this setting. So suppose is arbitrage free. So let me define the function we want to maximize. So let's call it V for value function. A, which is nothing else than the expected value U applied to 1 plus r, then our initial capital, plus a scalar product multiplied with the discounted returns. And a is a vector in RT. So this is the target function we actually wanted to maximize, or we will still want to maximize, over all values of a. And now we recall, this is since, or what was our observation from the last proof already. So if I consider such an a in RD, take the scalar product with the discounted returns, and then I do my usual decomposition into a part of a which is in L and some other part which is in the complement of L. This is nothing else than the scalar product of taking only the part in a which is in L with the discounted returns. Right. Therefore, it is sufficient to maximize the a over a in L. Right? Instead of considering the whole RG, we know we only need to consider all these vectors in L, because the other one, they are not contributing to our returns. Okay. All right. Okay. So now we want to use that our utility function is actually bounded from above. So what does it mean? So let's take a constant c, which is supposed to be an upper bound for our utility function. So such that if I consider the utility function evaluated at any point y, it is supposed to be less than c. And this is possible since we assume that utility function is bounded from above. Okay. So what does it imply? So if I take now a lambda, and I'm allow myself to send this lambda then to infinity of v, v is the target function we have defined, and then I consider lambda multiplied with the vector a. Okay. So what is this? We estimate this from above by, well, I have here my expected value of u applied to 1 plus r multiplied with the initial value plus, now I have a lambda times a multiplied with the discounted returns. Two brackets. And let me restrict this to the case that my returns are negative. So a times is negative. And now there's missing something because the returns might be also positive. So all the other cases I estimate by c. And now if I take the limit here and know that this is negative, well, this goes to minus infinity. since I know my utility function is strictly increasing, increasing, and concave. And this implies that if I take the limit of y to minus infinity of u, then this is minus infinity. Right? So if I take any trading strategy, so meaning here constant or RD, and I scale it up to infinity, well, I can make sure that I mean my utility, expected utility goes to minus infinity. So this basically tells me I should not take too big trading strategies, or too big position in the market. So let me fix now lambda and introduce you the set f of lambda, which is the set all a of in L, right? L was the linear subspace we actually care about in our maximization problem, because the rest gives us anyway 0. And I consider only those A in L which have the norm equal to 1. And if I consider my value function V, and then lambda times L should be bigger than 0. Because I mean, we are looking for a maximum, so if 0, so we are only caring about those trading strategy A in L, which in the end give me at least more than doing nothing. Okay. So why is this now a nice set? Well, first, let us take the concavity of our value function. And this implies that, well, if I consider V evaluated alpha times A minus 0, so this is the condition we formulated on the right, minus U, well, this is by the concavity, this is less or greater or equal, oh, sorry, this is greater or equal than alpha times V applied to A minus 0. And this is nice because now we can order these sets of f lambda. So f lambda is strictly increasing, strictly shrinking if we make our lambda bigger. If lambda is less or equal than lambda prime. And now, so we have this order. Now we recall here that if I make my lambda, I mean, if it's sent it to infinity, then the value function goes to minus infinity. So this is 6.3, 6.4. So by 6.4, 6.4, we see that f of lambda goes from above to the empty set as lambda goes to infinity. And such, there exists actually natural number and 0, such that this is the empty set. So lambda 0, f of lambda is the empty set for all lambda which are bigger than n. Right? So if you go here to 6.4, you see at some point you hit the level where you're worth then the value function valued at 0. And in this moment, you don't care about these values anymore because we wanted to find the maximum. And if you know you're worth then the 0 strategy, you don't need to look there anymore. So this implies b of a is less than b of 0. What I said, this is for all L in A with the norm of L here. So what you see, if we only care about the optimization problem over L, because everything which is in complement doesn't contribute to our gains. And secondly, we only care about trading position which have a norm less than n0, because everything else gives us a worth value at the end than the 0 strategy. So what do we learn from this is, well, in order to find the maximum in, this is 3 points. So our optimization problem P, right? So we briefly go up again. So here in orange, our optimization problem. So in order to find an optimization problem, an optimizer or maximizer to this problem, 6.3, we only need to maximize over A in L, and we only need to maximize over all A which have a norm less than an n0. Okay, and this is rather nice because, well, it is enough to maximize the continuous function v, which is our value function, over the compact set A in L such that the norm of A is less than n0. In other words, there exists maximizer A star to our problem. Okay, so if the market is arbitrage free, we can always find a maximizer. Now we want to say, well, if there is maximize, then the market has to be arbitrage free. And this is so often done by a contradiction argument. So let's suppose there exists an arbitrage opportunity. And now what does it mean? So this is by our last lemma. We know that there exists such an ether, D such that if we take this position ether in the market and the returns are always non-negative and the returns are strictly positive with a positive probability, right? So this is, which is means to have an arbitrage opportunity equivalently characterized by our previous lemma. Okay, and now let's take a maximizer, which assumes this exists by assumption. So let us take our the maximizer. To given some initial condition, some initial capital. Right. All right. So this is what we have. So what do we observe here? If I take now this maximizer, and I also take my arbitrage opportunity, ether, and I plug this into my value function. So in my optimization problem, so what is the terminal wealth we can generate it? So we take the position A star, because we know that this is the best we can do. And now we assume that we have an arbitrage opportunity ether. So we follow this as well by trading the market. Right, and now I need to count the brackets. That's yeah, one more. Well, this is strictly less than if I just follow my strategy, which is supposed to be my optimal one, so A star. Right. Since my U is actually as a utility function, so I know it is strictly increasing. And this is an issue because this contradicts let me write. This contradicts the optimality of A star, right? Because, well, we found if we have an arbitrage opportunity, we can take any maximizer of our utility problem A star and add this arbitrage strategy to get some higher expected terminal utility. So the moment we know there is a solution to this portfolio optimization problem, the market has to be arbitrage free. All right. Right. All right. Okay, let me conclude this section with a little remark concerning this last proposition. First remark is this is remark 6.14. Okay, first let me give you an example. The last proposition applies, for example, to u, so the utility function chosen to be minus exponent of y. So take an exponential utility function here. It's one example of an utility function which is bounded from above. And the second remark I would like to give you is, okay, the assumption that u is bounded was not laziness, it's actually essential for this proposition to hold, is unbounded from above, then our proposition is not true anymore. And well, this is what you're invited to study on the problem sheet. All right, so assuming here the assumption, I mean, making the assumption that the utility function u is bounded from above, it's not laziness, it's a necessary assumption. Okay. Okay, so much concerning the utility maximization problem with one trading period, and now we want to understand how we can solve the problem in a general market, so with several trading periods. So let us come back to the portfolio maximization problem. On multi-period market. Okay. And to give you right away, the idea is now, this is usually referred to the dynamic programming principles, is to iteratively solve this problem, your portfolio optimization in the one period submarkets, and then obtain under suitable conditions a global optimization or a global optimum by adding or pasting together these local optimal solutions. So what do you mean? Okay, so what do we consider? We consider a general market, so general time index set is T as usual. And well, the point is, of course, that we have more than one trading period. And what we want to assume, this is what the new assumption is, in order to be able to solve the problem, the global optimization problem by considering the local optimization problems in one period, we need to have some independent of the path, which is can be done by assuming that the underlying price process is a Markov process, as you might have heard or seen already. So if you haven't, it doesn't matter, because we make a slightly stronger assumption by just assuming that the discounted returns are independent. And independence is something everyone has seen. Okay, so we fix the probability space. As usual, and we assume that the random vectors so as usual, so our random returns, this is D plus, and then we have, now we have T trading periods, so we have also T vectors of random returns modeling the returns of these trading periods. Are supposed to be mutual independent, pairwise. Mutually independent. And this is not an assumption I just make for fun. This is actually an assumption I will use. So keep this in mind. And well, with the price process, these are the de-risk asset. It's now given by, so we iteratively define this. So the price at time t is given by right, so t, and this just means, right, if you, I mean, where this definition are coming from? Well, we have defined the returns, and this generates our price evolution. This is where it's coming from. And T, okay. So what we say, okay, we assume that the discounted returns are independent, and these discounted returns in each of these trading periods determine the price evolution. Yeah. Okay. And now, just a remark for those who have seen it, Markov processes, and this is actually what I need here. Okay. So this is just a side remark, which is not super important for the understanding of the rest, but but by making this decision, we ensure actually that the price process is a Markov process. Okay. Um, why do we care about this Markov process, or what does it say? The Markov process is the heuristic process. We formulate the idea that the current state is independent from the past. And why do I care about this? Because this me has the advantage that, well, we can reduce the global optimization problem to a one-step optimization problem, because we can make our trading decision just based on the current information we have. So if we want to invest in the market at time t, we look at the capital we have at time t and decide how we split it up into the d+1 asset. The advantage it is efficient to consider trading strategies of the form so C at time t is just a function f which depends on the current state. So this is the decision rule we based, so how we split up our capital, and this means we take our capital we have at time t and we split it up into to put the different amounts into the different assets. And then this is, we have to do at time 0 up to time t-1. And at time t, we don't need to rearrange our positions anymore because what the terminal time we have. And you see here, so the trading decision is independent of the path values of my capital. Right? So if I had at time 1, I just base my trading decision on the amount of money I have at time 1 and not anymore on the amount of money I had at time 0. And to make everything well defined, we need to have at least a measurable function. Which takes the capital and splits out the position. So this ft is here called decision rule. Right. Right. So if I fix this function ft, this tells me, okay, the moment I have, I know my capital at time t, ft tells me how I split it up into d position. So let me give you the definition. Definition 6.15. Right. So an investment policy P is a vector of decision rules. Right. So investment policy is, well, a vector of the decision rules I make, so how I split up my capital at each time, vector of decision rules T. And now, won't surprise you, right? These vectors, I mean, just for fixed further notation, is a function depending on x. And this decision rule tells me how much money I have to invest or want to invest in this de-risky asset, depending on the capital I have time t. And so, just a remark here, what the financial meaning. This tells me, well, K T stands for the amount invested at time t in the K risky asset, depending on, well, the capital you have. Well, x at time t. Okay. So what is now our optimization problem we want to solve? So again, if we want to talk about an optimization problem, a utility optimization problem, which we have here, we need to fix a utility function. So this is my utility function. Utility function. And what we learned, what we want to do is we want to assume that it's bounded from above. So now, just to recall, it's a given initial capital. We want to come back to our portfolio optimization problem, which was as usual denoted by P, which tells me I want to maximize of all decision rules, investment policies now, okay, here. So this is the investment policies I'm considering. Rather simple. I want to maximize U over all, I mean, over the terminal values, which I get from this, from trading with respect to this investment policy. And as usual, I want that my initial value is given by my given initial capital. Right, so this is where the maximum is taken over all investment policies. Pi. Right, so this is now SO. Before the optimization, portfolio optimization problem I want to consider. Right. Now, let me screen. So note, I mean, what is, if we want to understand here this terminal wealth generated by the investment policy, so what do we note? I mean, at time 0, I mean, this is given by the problem, right? So we have the initial capital x0, so that's easy. And at time t1, so we just use our iteration formula I recall at the beginning of the lecture. So this is 1 plus R1 multiplied with the initial capital I had, plus I take my position in the market, and then what I have at time 1 depends on what my discounted returns do. And now I can iterate this procedure up to time t, or even capital T if you want to, and realize, well, at time t, the wealth I have is given by 1 plus R multiplied with the wealth I had at time t minus 1, and then I split up based on my decision rule f t minus 1. I split up my capital into d positions. And then what I have at time t depends on the returns in this trading period, or the discounted returns in this trading period. Right? And now these returns are all independent. So I'm basically, if I iteratively maximize the returns, or my value, sorry, my capital I have in each period, then these are independent portfolio optimization problems. So the idea, let me idea or approach is to solve P for each one period submarket, and combine these local solutions to obtain a global maximum or maximizer. And this is this idea, why not red, is usually referred to the dynamic programming principle, which is a standard approach to deal with such optimization problems. And this works often rather nicely, I mean, pretty nicely, as long as you're in a Markov setting, so that you have the underlying independence to need to apply this idea. Okay, so So what do you mean local? And so let me make this idea here more rigorous, because this is not how we can set up a proof. So we need to make it properly. So this definition 6.16. So we define J t, so which is the function. So the J at the terminal time t is just our utility function. And well, if I take another t, and another axis, right? So we J t to be the supremum over those partition rules, which are, overall investment policies. And now I want to maximize the utility, the expected utility of the t, given that I have at time t the capital X. Where the supremum is taken over all investment policies pi starting at t with the capital X. Okay. Right. So this JT then X, which is function, so X is a real number. So this is called value function. Value function at time t. And well, okay. What else? And if we have an investment policy P star, which consists of F star 0 up to F star t minus 1, such that the expected utility of the terminal wealth generated by this investment strategy P star, given the initial capital X0, is equal to J at time of J0, so the value function at time 0 evaluated at X0, then P star is the optimal investment policy. For P. All right. Okay. Okay. All right. Okay. Let me stop here before we come to the proposition really characterizing the solution of the optimal portfolio optimization problem P with this dynamic problem idea. So the idea I formulated vaguely here in orange, they will become mathematically clear in the next proposition, next theorem, and its proof, right? This is the meter idea we want to apply then to solve our portfolio optimization problem P. And for this purpose, we introduced this value function and the optimal in order to find the optimal investment policy. All right. Thank you for watching the video.